In this video, we'll see how to find the coordinates of the point of intersection of two lines written in their three-dimensional vector equations. Now we're given two lines here. The first is xyz equals to -2, -1, 0, plus alpha times the direction vector 1, 1, 1. The second is the line xyz equals to 8, -6, -11, plus beta times the direction vector -2, 3, 5. Now, to find the point of intersection, the first thing we will do is to write each of these line equations in their parametric form. So, the first line equation would have parametric equations x equals to -2 plus alpha, y equals to -1 plus alpha, and z equals to alpha. That's the parametric equation of the first line. For the second line, we would have x equals to 8 minus 2 beta, y equals to -6 plus 3 beta, and finally z is equal to -11 plus 5 beta. Now that we've done that, our next step will be to equate each of the expressions for x, y, and z in both of these line equations. That means that we'll equate -2 plus alpha with 8 minus 2 beta, as well as -1 plus alpha with -6 plus 3 beta, and finally we'll equate alpha with -11 plus 5 beta. Doing so results in -2 plus alpha equals to 8 minus 2 beta, -1 plus alpha equals to -6 plus 3 beta, and alpha equals to -11 plus 5 beta. We now have three equations with two unknowns. We'll rearrange this a bit so that we have the unknowns alpha and beta on one side of the equation, looking like something like this. Alpha plus 2 beta equals to 10. Alpha minus 3 beta equals to -5. And alpha minus 5 beta equals to -11. And just as we always should, we'll name each of these three equations equation 1, equation 2, and equation 3. Now, to solve these three equations with two unknowns, we'll use two of these three equations to attempt to find alpha and beta. We'll then use the third equation to verify or check whether or not that solution we found, if we found one, is viable. So what we'll do here, we'll start by using equation 1 and equation 2 to attempt to find alpha and beta. So we fall back on a typical scenario of two equations with two unknowns. That's alpha plus 2 beta equals to 10. That's our first equation. And alpha minus 3 beta equals to -5. That's our second equation. Now, to do this, what we'll do is we'll eliminate alpha in the second equation, and we do this by subtracting E1 from E2. So we'll just write equation 2 becomes equation 2 minus equation 1, and we write this below. So the first equation would be unchanged, alpha plus 2 beta equals to 10, and the second equation, well, if I subtract the first equation from it, alpha minus alpha is 0, and -3 beta minus 2 beta would be -5 beta. On the right-hand side, we would have -5 minus 10, which is -15. And we quickly see that this leads us to beta equals to -15 divided by -5, so beta is equal to 3. Our first equation therefore becomes alpha plus 2 times 3 equals to 10. And the second equation is still beta equals to 3. And we quickly see here that this leads us to alpha equals to 10 minus 6, so alpha equals to 4. So those are our two potential values for alpha and beta. Now, as said previously, we turn to the third equation, so that would be equation 3, to check whether or not this solution is viable. So equation 3 is alpha minus 5 beta equals to -11. And if we focus on the left-hand side, LHS, left-hand side, if alpha equals to 4 and beta equals to 3, the left-hand side would be 4 minus 5 times 3, which equals to 4 minus 15, which is equal to negative 11. And therefore we can see that the left-hand side and right-hand side of this equation are equal. This means that this is a viable solution, and these two lines do in fact have a point of intersection. To find the coordinates of the point of intersection, all we need to do is either replace alpha by 4 in this first line equation, or beta by 3 in the second line equation. We'll go ahead and use alpha equals to 4 inside the first line equation. Doing that, we find x, y, z would equal to negative 2, negative 1, 0, plus 4 times 1, 1, 1. That's negative 2 minus 1, 0, plus 4, 4, 4. And we find the position vector 2, 3, and 4. So the coordinates of the point P, of the point of intersection of these two lines, would be P with coordinates 2, 3, and 4. And you can go ahead and try for yourselves. If you replace, not alpha, but if you replace beta by 3 inside the second line equation, you'll find the same answer. And in fact, let's go ahead and do it. We should have x, y, z equals to 8, negative 6, negative 11, plus 3 times the direction vector negative 2, 3, 5, leading us to 8, negative 6, negative 11, plus negative 6, 9, 15. And we quickly see that this is the same point, 2, 3, and 4. So indeed, the point of intersection of these two lines is the point P with coordinates 2, 3, 4. And there we go.